Hey folks! In the previous experience, we talked about discrete random variables, and now we're going to make the shift over to continuous random variables. And that's going to be largely the main focus of the rest of our course is focusing on analysis of continuous random variables in various ways. And as a reminder, a continuous variable is a variable that it doesn't necessarily come in whole numbers, right? You can have half of a value, such as inches or pounds, and contrast that with discrete random variables where you can only have whole numbers. So we're going to talk about probabilities associated with continuous random variables today and for quite a while actually. Continuous random variables are represented with a graph, and if we want to find probabilities associated with that variable, then we call these probability density functions. And it works quite a bit different than what we saw with discrete random variables, because in a probability density function, in order to find probability, we use the area in a graph to represent that probability. So for a quick contrast here, like with a discrete random variable, like we saw in a previous video, we might have probabilities explicitly written on the vertical axis, and we might have values of our variable on the horizontal axis. And we saw that, well, you just get the probability from the height of these graphs, of these bars. And it's a very explicit way to just determine probability. It's a bit different in a continuous world, because what we're going to see is that we have these smooth curves, and one of the main ones we're going to look at is a bell-shaped curve. And if we want to find probability, we actually need to find the region that's shaded here, that area. So that was a quick digression intro, but this type of graph, the vertical axis is not called probability, but is called density. And it's just a different little world for continuous variables. Now, a bell-shaped distribution like this, we're going to discover techniques to find that area. We do know the empirical rule, but there are other ways. But to make our leap to a continuous world, for today, we're going to focus on, what's called a uniform probability density function. And then in the next video, we will sort of start building up our confidence to talk about bell-shaped density functions, and that's going to be the jam. So let's talk uniform. We've mentioned uniform distributions in the past. Remember, a uniform distribution is one in which the heights of, if we were thinking about a frequency histogram, the heights are all roughly the same. All the frequencies are roughly the same. But we're going to consider this in a continuous perspective, in which we would probably smooth out that curve a little bit, and it would be kind of a flat top. Let's look at a specific example of a variable that follows a uniform distribution, supposedly. All right, let's take a gander at this example. Suppose the amount of time that a person waits at the DMV, Department of Motor Vehicles, is uniformly distributed between 0 and 30 minutes. Okay, we're going to draw this uniform probability density function. So I've laid down a set of axes here, and as mentioned just a few minutes ago, that the vertical axis is called density. So I will label the y-axis as such. The horizontal axis is always our variable. And here we're talking about the amount of time that someone waits at the DMV. So maybe we should let the letter X represent the waiting time in minutes, wait time. And now that I've got X, capital X, defined, I can just label X down here. And at this DMV, you wait between 0 and 30 minutes. So we've got 0 at the origin. That works for me. And we're going to have 30 minutes over here. Okay. A uniform distribution, hi buddy, is a flat top. So this is not going to have the bell shape. That's not uniform. We're going to have basically a rectangle. And I can draw straighter than that. Maybe not. And this is a rectangle from 0 to 30 minutes. You may recall from our previous probability videos that all of the probabilities must sum to 1. So in this graph, it's just a rectangle. The total area here must equal a 1 if we're going to allow area to represent probability. So this brings up a fun little question. What must the tick mark on the vertical axis be right here? And this is a rectangle, it's a flat top approximately. So we need a number right here such that in order to find the area, remember we do length times width to find area in a rectangle. We know the length is 30. So what must the width be in order for the area to equal 1? What's the width? Well, or the height. What cancels with 30? It would be 1 over 30. So this height, not drawn to scale, the height of this density function would be 1/30. Using this uniform distribution, let's find some probabilities. I got some questions queued up here. Let's find the probability that you wait at least 20 minutes. Okay, so we want to represent 20 minutes along this x-axis. I know 15 would be right in the middle, so maybe 20 would be right around there. And I guess 25 would be right around there. At least 20 minutes. I like to represent the region that we are searching for. I like to shade it. So I'm going to shade, because it says at least, I'm going to shade to the right of 20, because that's at least 20. It would be 20 or greater. So this shaded region is what we are trying to find. That is the area. So we want to find the area in the blue region, the light purpley blue. And so we want to think about the length and the width of that region. Well, from 20 to 30, isn't that a length of 10? And the height of this rectangle, well, it's always going to have the same height, so that's 1 over 30. So our area here is 10 over 30, which is 1/3. Or if you prefer a decimal, 0.3333333. And that's our solution. So there is a 33% or a 1/3 chance that you would wait at least 20 minutes at the old DMV. Okay, I'm going to clear my little drawing space so we can do the next question. Next question. We want to find the area, because that's probability, of waiting more than 25 minutes or less than 10 minutes. Again, I'm going to put some tick marks to make this a little easier for myself. Every 5 minutes seems pretty reasonable. Okay, so this question, in essence, it's like, all right, what's the chance that you wait a pretty long time or not that long? So I want to represent this area in my little image. So less than 10 minutes, that's going to be to the left here, or more than 25 minutes. Okay. Or, remember when we talked about the addition rule, we're going to need to find these two areas and add them up. They are disjoint. They can't happen at the same time, right? You cannot somehow wait only less than 5 minutes and have that also be more than 25 minutes. It doesn't work like that. We need to find these two regions. We'll add them up. We know that they both have height 1/30. And we'll do the one on the left first. Well, the height is 1/30, but the length is 10. And we'll add. The other one also has height 1/30, but its length is only 5. Okay, so here we've got, I might actually keep my common denominator. We have 10/30, which is certainly a third, but over here we've got 5/30. And I've kept that common denominator so that I can see that this is 15 over 30, which is the same as 1/2. And it looks pretty reasonable. That it looks like I have shaded about half of this region. I got one more question for you. Okay, I've scrolled down a couple clicks. Let's find the probability of waiting exactly 15 minutes. Exactly 15 minutes. Okay, area, that's the jam. I'm going to try to represent this. 15 minutes. I'm using red. There's nothing really to shade there, is it? Because exactly 15 minutes, it's not a region that encompasses an area. It's only one-dimensional. Here, there is no area. Area equals 0. Therefore, the probability of waiting exactly 15 minutes is 0. And the reason for this is because we're in a continuous world. There are an infinite number of possibilities here. And the probability of observing one out of infinity it's so minutely small. We don't even write that really. It's so minutely small that we consider that 0. But an easier way to think about it is that there's no area when we are considering a precise value of our variable. Contrast that with the previous 2 examples. These encompassed regions, at least 20 minutes. That wasn't just one value, it was a range of values. And same thing over here. So this brings up an important point. When working with continuous variables, we need to always consider the variable over an interval of values, such as more than 20 minutes, less than 10 minutes, in order for us to arrive at area, which is our proxy for probability. So that concludes this introduction to continuous random variables. One of the main ideas is that we are using area as a way to determine probability for continuous variables. We wanted to use the uniform distribution first because it's just a rectangle, so finding area is pretty easy, length times width. In the next video, and for the next several videos, we're going to talk about bell-shaped or normal distributions.